Hello everybody. Today we're going to be covering an example problem with dealing with an isentropic turbine. So I've taken the time to sort of compile my columns here, depending on what we're dealing with, right? So I have the first state here. This is for, okay, first of all, let me read the problem. It'll also be in the description. Steam enters an adiabatic turbine steadily at 8 megapascals and 500 degrees Celsius and leaves at 1000 kilopascals. If the power output of the turbine is 5 megawatts and the isentropic efficiency is 70%, determine A, the mass flow rate of steam through the turbine, and B, the temperature at the turbine exit. Now, first of all, what we want to go ahead and do is identify a system. Now, I'm just going to write it up here to give us space. But the system is an adiabatic turbine containing steam. Pretty straightforward because they give it to us, right? You can even write H2O, containing H2O, right? That's water. Wow, I really slanted that. Well, that's the first part, right? Remember, they're gonna want us to have a system, sketches including state diagrams like a PV or a TS diagram, conditions, physical laws, properties, and our calculations, right? Now what I'm gonna go ahead and do is compile my tables and try and fill up my table as much as possible. Now I know that the inlet pressure is 8 megapascals and the inlet temperature is 500 degrees Celsius. So what I'm gonna do is go to my table A5 and find what state it's in. And when I do that, I'm gonna find that it's actually a superheated vapor because this T1 is higher than the T saturation for this pressure, right? So I go to table A6 for my superheated water, right? And I find 8 megapascals, which is the same thing as 8 megapascals actually. You don't need to know that. Or you should know the 8 megapascals, the conversion rates and everything, but you just go to 8 megapascals on table A6 and you find 500 degrees Celsius. Now what it looks like is my V is 0.041767. That's meters cubed per kilogram, right? And we keep doing this with all of our properties, right? With our H, our U, and our S. And I went ahead and found these. You might not need them for the problem, but I don't want to have to keep coming back to my textbook or back to my tables because we're limited on time during an exam, right? So when I fill out the rest of these, I'm gonna get boom. So that's what we have, right? When we fill up our table, these are the values you should get. Now, it sort of differs on some tables sometimes, but you should get numbers around these, right? Now, they're asking us for the mass flow rate of the steam through the turbine. And first of all, we have to assume that what they're talking about is the actual mass flow rate rather than the isentropic turbine. I'm going to use the actual values to find that, right? So first of all, what I know is, okay, so let's write our open system equation for a turbine. So we get this, right? Pretty simple, right? And when we rearrange it, right, we get this. Solving for work out, we get this, right? And they've already told us that this, our isentropic efficiency is 70%, right? That's the same thing as saying 0.7. So what we can go ahead and do is, so isentropic efficiency, as we know, right, for a turbine is equal to work actual over work isentropic, right? And we can equally say this. Small WA over small WS, or big WA over big WS, right? Basically just saying that like the work over the work is equal to that 0.7. So what we can go ahead and do, right? We can go ahead and say this. 0.7 is equal to, actually, you know what? Let me do this. Let me go ahead and divide through by m dot on both sides. And that leaves me with work out, right? and that's H1 minus H2. And equally, like I just said, right, that work out, I can equally say this, right, for a turbine. So what I can go ahead and say is that the isentropic efficiency is equal to H1 minus H2A over H1 minus H2S, right? It's pretty straightforward. I hope you understand why I did this, because this actual state, right, it can either be work dot or the actual work that we're dealing with, right? Actual work over the isentropic work. That'll give us that isentropic efficiency. So we can easily say this. And one thing we also know, right? So this is my column for the actual outlet of the turbine, right? This is the isentropic outlet that we're dealing with. So what is the same in an isentropic process from the beginning to the end? Entropy, right? So that being said, this S2S is going to be the same as this 6.7266 because it's an isentropic process. So we can easily say that S2S is equal to 6.7266, the same as that S1 that we're dealing with, right? Now, why do we need that? Now, since I have my pressure and one of my properties, I can go ahead and find what state it's in. So I'm going to go to my A5 table and find the state that it's in. And what I'm going to find is that it's a superheated vapor. So I'm going to go to my table A6 for pressure, right? And I'm going to find 1,000 kilopascals, which is the same as 1 megapascal. So I'm going to flip to 1 megapascal, and I'm going to find what I'm going to look for is the entropy that's closest to this. Generally, for us, they didn't make us interpolate. They said choose either value. Choose the value higher than it or choose the value lower than it. So for entropy, right? So what I do is I find 1,000 kilopascals, right? And what it looks like, right, is that the closest, when I'm looking at the entropy column, right, the closest value to my 6.7266 looks like it's 6.6956. So I'm going to use those values for my other values, right? Because we don't have to interpolate during this exam. It would take too much time for us to interpolate. So we can just choose the nearest values. And it looks like that's the value at 200 degrees Celsius. So I'm going to go ahead and write those values. I'm going to find those values that I need to solve this problem. I made a mistake. You have to be really careful when dealing with these columns because you see here, I made a mistake on my, I used 250 for one of the values. I used 250 for my value of V rather than like 200, right? So you have to be very careful. But I'm glad you see me making mistakes so that you can know what to watch out for. So the actual value of 200 is this, 200 degrees Celsius. And that's what we should have, right? Let me just double check myself quickly. Yes, that's what we should have, because that's what we had for. I went to 1,000 kilopascals, right, which is the same as 1 megapascal. I found the entropy that was closest to the entropy that I know for sure. I know for sure this is correct because we're dealing with an isentropic process, right? So this entropy has to be the same for the isentropic turbine, right? So I went and found the value, the column or the row that had the closest entropy value to this entropy, right? And I went ahead and used those values for that entropy. So now, since I have my H2S, right? I have my H1, my H2S. So the only thing missing, and I have my isentropic efficiency. So the only thing missing now is my H2A, and I can go ahead and solve for that. So I end up getting this. 0.7 is equal to I don't have to write H2S there, right? Because I know what my H2S is. So that's 28.3. And with this now, I can go ahead and solve for this. So when I subtract these two and multiply it out, I get this. So my 339, you know what, I'm just gonna go ahead and solve for the whole thing. It's simple algebra, and I'm sure we know how to flip the numbers around and everything. So what I end up getting is that my H2A is equal to 2999.6 kilojoules per kilogram. And a good way to check yourself, right? If this were true, right? The difference between these two numbers has to be smaller than the difference between these two numbers, right? And once you match that up, you'll see that that's the case. So 2999.6 kilojoules per kilo, right? And now what I'm gonna go ahead and do is go again to my table A5. You're gonna use a lot of tables. It gets sort of repetitive at a point in time. But I'm gonna go to my table A5, find 1,000 kilopascals, and find my find if my HG, if this is bigger than HG, and it is indeed bigger than HG. So I'm gonna go to my table A6, right? Go to 1,000 kilopascals, which is 1 megapascal, and find the closest value again, since we don't have to interpolate, the closest value of H2A to this H2. So once I get that, it looks like the closest value is 2,943. So that looks like 2,943, which is at 250 degrees Celsius. So I'm just going to use that row for the rest of my values, right? And once I do that, I get my V is this.
Okay, guys, so then we have 7 minutes. I'll just go as far as I can go.
Hello, my name is Tiffany Murray, and today
See, I keep making this mistake. You have to be very careful. We're looking at 250. I use the value for 200. And the good way to match it up, you have to know that these are going to be different, since we're using 250 and 200. So with 250, I'm actually going to have these values.
let me take this opportunity to give a bit of disclaimer. Today I will be giving you tax or investment advice or anything like that. Today is educational for educational purposes only, so just take it for today. As an overview, today we'll discuss the following. What is budget? Budgeting mistakes, budgeting goals, short-term goals.
And that's what we should have, right? So now what we can go ahead and do, right, is find that we know some certain things for turbines, right? When we solve for workout and everything, right, we get this. So I know that my work actual has to be equal to H1 minus H2A, right? So with that, I know my work actual, which is 5 megawatts, right? So I know that 5,000 kilowatts is equal to 3399.5 minus H2A, which is my 2999.6, right? Wow. Oh, I'm sorry. Actually, it's this M dot, right? What we have is actually this.
So that's the difference between the Plain Hampshire
I forgot that m dot because we divided through here. But we have that m dot, and that's what we're looking for, right? So when we go ahead and solve, we get this, dealing with the actual turbine, right?
Yes, so sort of your bills or any items that come up during the month that you need to pay for.
And then we have H2A.
Anything that financially.
And then when you solve for m dot, you should go ahead and get.
Okay, so let's talk about common budgeting mistakes. So you'll see listed up here on the slides that the first one is not tracking your spending. So how do you think not tracking your spending would affect you as far as creating a
You
budget?
should get 12.5.
12.50,
I should say.
No proof of what's being.
So that's the first thing we're looking for, right? And then they also asked for the temperature at the turbine exit. We've already found that, which is why I go ahead and write down all of my values and everything. So our temperature at the turbine exit is actually 250. Since they're not asking for the isentropic turbine, we go ahead and assume that it's the actual turbine. And that's really all you need to do to it. It's a lot of repetition going back and forth between the tables and your work, the tables, your work and everything. And then that's what you should end up getting, right? But we're not done just yet. So, oh, wow, I probably shouldn't have erased that, but it's okay. What we have, right? We still have to write out, we still have to draw, sketch and everything. So since we're dealing with water, we're gonna have a sketch for a substance changing, a phase changing substance, right? It's gonna end up looking something like this. So here, it's gonna be ideal to draw a TS diagram. And the TS diagram looks something like this. So what we know, right, is that it went from, so okay, first of all, what you're gonna end up having is two lines, right? For the first pressure, and then the second pressure, right? And then this is T, this is S, right? So you're gonna have the first pressure and then the second pressure, right? And then we know that we went from superheated to superheated again, right? So what we started at 8 megapascals and we ended at 1000 kilopascals, right? So this line is gonna be for 8 megapascals. And this is going to be for 1 megapascal, right? And then we start out somewhere here, right? And then for both the actual and the isentropic turbine, we ended in the superheated state, right? So what you're going to do for the isentropic process, you're just going to draw a line straight down. And that makes sense, right? Because the entropy stays the same throughout the process, right? But we still end up as a superheated vapor. But for the actual process, you're going to draw something that looks like this. And it curves, right? It's not just a straight line. So what we're going to have here is state 2A, and here state 2S. That's state 1, right? So it makes sense, right? Because we went from superheated to superheated, and of course, for an isentropic process, we're gonna go straight down, no change in entropy, right? So that entropy is constant. However, entropy always increases during the process, right, for an actual process. So that's why this entropy gained. Let's say we had gone from we started with a compressed liquid or something. That entropy would have gone like that, right? So it always goes to the right for an actual process because that entropy is increasing, right? Makes sense. What else do they need? They need the conditions, right? Steady state, adiabatic, no change in entropy for the isentropic turbine. Yeah, I mean, really, single stream. Just assumptions that you're gonna make to help you get through the problem a little bit smoother, right? For physical laws, we used the open law first system equation. We went ahead and used. To be honest, okay, we went ahead and used this equation. We went ahead and used. That's really it. If you want to draw like steam tables, I don't know if they'll give you credit for that, but yeah, that's really it. So this is really all you need to solve the problem. If you have any questions about what I did, go ahead and leave them in the comment section. Please don't forget to like and subscribe. there'll be more videos out there and everything. So let's keep learning thermal. Thank you.